everybody, my name is Jordan Paline, and today I'm going to be presenting on the jet engine electrical power generation cycle for Group 2. Okay, so electrical power generation, we have two different modes. We have base power load, then we have peak electrical production. Base power comes from mostly coal, nuclear. However, whenever our energy grid has peak values, peak requirements that we need to produce additional power, we will implement gas-powered turbines. So these are similar to what we're going to be looking at today with a jet engine. So jet engine cycles, we have a TS diagram and a PV diagram. So we can see from 1 to 2, we have an isentropic process as long as 3 and 4, and then 4 to 5. Those are isentropic processes as well. And then we have constant pressure lines from 2 to 3, and then 1 to 5. This is a diagram showing our apparatus today, where we have air intake, we have compression of our air, then we have a compressed air goes into our combustion chamber and mixes with our fuel, combusts, spins around in this turbine, produces thrust. This thrust is then dispersed over a cone, and that thrust spins as a low pressure turbine, which is our power turbine, free turbine, which drives a shaft and induces a current in our electrical alternator, which generates electrical current, which gives power. Measure values of interest. So these 5 states that we have each have a temperature and pressure relating to the air. So if we can find the values at those states, we can use the ideal gas laws and then the isentropic values in the air tables to determine their specific enthalpy values. Our apparatus for collecting this data is our TurboGen software. This measures the values that those 5 states with their values every point in the cycle. The fuel today is going to be kerosene, and we have a few values of kerosene here. We have the energy content, so this is the amount of energy that we can get from a set amount of fuel. And then our kerosene density, this will come into play whenever we're doing the mass flow rate of our fuel towards the end. Operational zones, so we have this lever, which is our throttle, which controls the engine RPM. We want to hover around 40,000 on startup, and then we want to increase to around 70,000 RPM. Then we have our brake, that we call it, which is also our load coming from our generator. And we want to stay around 8,000 RPM, and we want to keep a balance between these two. The following slide is going to be graphs over time with relation to inlet and outlet values. So on the left, we'll have pressures, and on the right, we'll have temperatures. We can see that there's a very low inlet pressure into the compressor, and then a sharp increase in pressure, followed by a very hard fall off where we end the cycle. And then our inlet temperature fluctuates between about 27 degrees and about 35 degrees. However, on the outlet of this compressor, we see that there's a very big increase on pressure, getting almost to 25 psi, followed by a sharp downfall. The compressor temperature also increases on the outlet as well, almost as an exponential climb. The turbine 1 inlet, the pressure is the same pressure as that we had in degrees Celsius, which is very hot. So this system can be very dangerous if not operated properly. Fuel flow, so we can see that there's very low fuel flow at the very beginning of the cycle, but then we do have a climb whenever we are reaching those higher RPM values, followed by the sharp drop where we end the cycle. So we need, this graph just shows that we are going to need more fuel to maintain a higher RPM value. Our engine and generator RPMs that we were talking about, we can see that we're maintaining between the 4,000 or 40,000, 80,000 RPMs, and then we're staying between our 8,000 RPMs that we were discussing earlier for the generator RPM. We don't want to get it too high. It'll cause our engine to have some fatigue failure. Current and voltage generation within the alternator, the exciter. We can see that these graphs will look very similar due to the fact that they're proportionally related. Power is going to be square root of 3 times voltage and current. So our graph, it would look very similar to those two, just multiplied by a magnitude value, which is that square root of 3. Our analysis point to determine the efficiency of the cycle, we're going to use the peak value, the peak RPM of the engine. All these values are collected from our data, and this value occurred at about 15,000 seconds. Specific enthalpy values, we can use H is equal to CP which is produced in this graph here. And these values match up very well with the thermodynamic tables. Using those enthalpy values, we can determine the specific work of the compressor, the work of the 2 turbines, the net work done by the power generation cycle, the thermodynamic efficiency of the cycle itself, and then also the amount of energy that we lost. And actually we can see that our efficiency is about 10 to 15%, which is very low. Inlet air properties, so these are the values with the inlet air to the compressor. As these values change, the rest of the cycle will change as well. We can assume air is ideal gas, so we can find the density. From second law, we can determine the inlet air velocity, and then also the mass flow rate of the air entering, as well as the volumetric flow rate. The Mach number is going to be the inlet air velocity divided by the speed of sound. We had 2 points of interest for the generator. We have a maximum current occurrence and then a minimum current occurrence, and this occurs at once we start revving up the throttle and increasing the load on the generator. Our minimum current values occur about 58,000 RPMs for the engine. Our speed ratio is going to be our N2 turbine over N1 turbine RPMs. Our resistance, which is just Ohm's law, is going to be R is equal to V over I. Our power is square root of 3, that magnitude times the voltage times the current. And then our specific fuel that's required to maintain this RPM. So fuel flow is given in liters per hour, so we need to convert that to seconds. And then same process followed for the maximum current requested values, which occurs about 70,000 RPMs for the engine. So in conclusion, maximum power generation is going to occur whenever current is maximum in the alternator. Our electrical power generation for the jet engine cycle itself is rather low compared to traditional values. And then also most of the energy is going to be lost to thermal heat in the system itself. My references, lab manual, thermodynamic textbook. And are there any questions? Hearing none. Thank you.